Sagorika, in this module 8, we are going to continue with where we left, namely starting with the ANOVA table, then going into the computation for the different sum of squares, having a relook at the computation of sum of squares for blocks unadjusted, treatment adjusted, as against that going for treatment unadjusted, block adjusted, computation of the expressions for the variances of the treatment difference estimates, etc., till we take up a very general description of the model from matrix point of view. So with this idea we are going to take up this module 8.
Sir, I think there is a counterpart of what you have said involving the treatment effects. Am I right, sir?
Yes, you are very right. We assume that the design is connected so that all treatment contrasts as also as all block contrasts are estimable. See, here is another version of the ANOVA table. I think this is what you are referring to.
Yes, sir.
In this version, we write treatments unadjusted, blocks adjusted, and then the errors come by subtraction. And then when we say treatment unadjusted, the sum of squares is the usual thing coming out of the CRD, and blocks adjusted, you get P prime D plus P, or P is the vector of adjusted block totals.
Yes, sir.
And this F ratio is good, is a valid F ratio for testing equality of the block effects contrasts. This P, as I said, is the vector of adjusted block totals, B minus N transpose R minus DT, and D is the matrix analogous to the C matrix, KD minus N transpose R minus Dn, and R minus D is of course RD inverse. Moreover, for a connected design, whereas rank of C equal to V minus 1, rank of D equal to B minus 1, this is an if and only if statement. That's why whenever the design is treatment connected, it is also block connected and vice versa.
Yes, sir. Sir, I am tempted to make a quick comment.
Are you referring to the computational aspect in the two tables?
Yes, sir. I believe sum of squares of error is invariant no matter how we look at the model and the decomposition into estimation space and error space. So, there are two ways of understanding the estimation space, but the error space is unique, and so...
Yes, that's why we can bypass direct computation of the sum of squares due to blocks adjusted and rather obtain it by subtraction, etc., etc. If you look at the two tables side by side, from one table you get the treatment sum of squares adjusted by going through the computation of C, C plus, etc. And in the other table, you simply transfer the error sum of squares and then you get the sum of squares due to blocks adjusted without going through any heavy computation. As you said, error sum of squares can be transferred from one table to the other, and sum of squares due to treatments unadjusted is very simple to compute. So the rest is obvious. Now you also have an answer to your earlier question. Take up the C matrix or D matrix, whichever is convenient to handle in terms of Moore-Penrose G inverse computation. Well, you must note that the computation of Moore-Penrose G inverse is a routine exercise, and in the process, eigenvalues of the C matrix are computed in case you have started with the C matrix. So let me continue. When the F ratio is significant, we may be interested in individual paired comparisons. For elementary treatment contrasts of the type tau I minus tau of I transpose I prime, we have tau I minus tau I prime estimated equal to etc., and the expression for the variance is given by this thing. Hence, we have available the usual t-tests. And the computation of the average variance of treatment contrasts, elementary treatment contrasts, that is the notation is V bar, average variance, that is the formula, and it turns out to have an expression like 2 sigma square over capital H, where capital H is the harmonic mean of the lambdas. This expression was obtained by Kempthorne in the mid-40s. V bar equal to harmonic mean of the lambda, inversely proportional to the harmonic mean of the lambdas. Lambdas are the positive eigenvalues of the underlying C matrix. Yes, Sagorika, here is a point worth mentioning. As you can see, computation of C matrix and derivation of its eigenvalues cannot be avoided altogether, since we are also interested in the treatment contrast estimates and the variance expressions, average variance, etc. So even though for the data analysis part, depending on whether you should start with C matrix or D matrix, we can avoid the computation of G inverse of the C matrix for the time being, but still when it comes to estimating the treatment contrasts, providing average variance expressions, we need to have the eigenvalues of the C matrix. Therefore, we need multiplied with the inverse of the C matrix as well. But I must hasten to add one important aspect of the data analysis in a linear model. You may still know it, but for the sake of completeness, let me take it up. I will refer to a block design for that matter. As you know, we use the triplet y, the vector of recorded observations as a column vector, then the model expectation of y, mu times 1 plus x b times beta plus x t times tau, and then sigma square I. Sigma square I refers to the distribution of the errors. And the mu times 1 is the vector of all ones, that is the constant general mean. Xb times beta, that refers to the allocation of the treatment parameters. Xt times tau, that refers to the allocation of the, the xb times beta refers to the block parameters. Xt times tau refers to the treatment parameters. That is the triplet, very important in linear model context.
Yes.
And with obvious interpretations of the matrices and vector parameters. We abbreviate it as y, x theta, sigma square I. Theta is the vector of all the parameters mu, beta, tau. First point to note is that all the error functions to enable us to estimate the error variance sigma square in the above model are necessarily to be derived from I minus px times y, whose expectation is a null vector. This P is very famous in the context of linear models. It is called the projection matrix. It is defined as P sub x equal to x prime x minus, that is the D inverse, times x transpose. And it is a routine exercise to work out expected value of I minus pxy given the model to show that this is nothing but a null vector. Therefore, I minus px times y, that is 0 expectation, and that is the only source of getting estimates of the error variance sigma square. You must be knowing that this px is an MMD matrix and rank of px is the same as rank of x, and further that because it is a projection matrix, its eigenvalues are 0 and 1. So this also explains the decomposition of y transpose y, the total sum of squares, as y transpose py plus y transpose I minus py. Whereas the first part refers to the estimation space, the second part refers to the error space. That's why y prime I minus py, that refers to sigma square. So the first term corresponds to the sum of squares due to estimates, and the second term corresponds to the sum of squares due to error, and error degree of freedom is nothing but rank of I minus px, which is n minus rank of x, and that is how we go for further computations. Sum of squares due to estimates can be viewed in two ways. That's because X matrix has the expression 1, xb, xt, and px can be computed in two steps. First you write x as AB, partition matrix AB, then it follows that px is nothing but PA plus 1 minus PA, P of B given A times 1 I minus PA. Whereas P of B given A, has got this expression. So there are two ways of looking at the expression computation of px. Either you start with A followed by B, or you start with B followed by A, and it depends on where A is landing, where A is combining 1 with xb, or A is combining 1 with xt. Depending on that, we have the expression for the sum of squares.
Yes, sir.
These are very standard derivations involving projection matrices.
I see. In that case, sir, we can interchange the roles of A and B and derive sum of squares of estimates as the sum of two components in two alternative forms. Further to this, I recall y prime 1 minus pay has a very simple expression. It simplifies to sum of squares of blocks unadjusted when A refers to blocks, and again it simplifies to sum of squares of treatment unadjusted when A refers to treatments. Oh, it is very interesting, sir. Sir, I believe that's how we also land into sum of squares of treatment adjusted and sum of squares of block adjusted when we get to the second expression in the above decomposition, as you have said, right, sir?
Yes.
So how does connectedness play a role in the whole derivations? I think I can figure this out myself. So let me try. When the design is disconnected, it amounts to decomposition into several connected components involving disjoint blocks and disjoint treatments. So, for a connected design, no matter how we do the computations, degrees of freedom attributed to block effects comparisons is B-1, and that for treatment effect comparisons is B-1. Is there anything more, sir?
Of course, you did not mention the vital point.
Okay.
The matrices for computation of sum of squares of the second part reduced to the C matrix or the D matrix as the case may be, depending on how you are looking at it.
Okay.
These derivations are nicely given in standard design books. For example, Ologde's book on design of experiments.
Okay.
An old but a bit difficult book in this area is the book due to M.C. Chakraborty. I'll stop now.
Okay, sir.
Sagorika, as you have noted, in this particular module, we basically started with our understanding about the ANOVA model and the computation of the sum of squares, treatments adjusted, unadjusted, blocks adjusted, unadjusted, roles of the two matrices, C matrix and D matrix, and their implication and their importance in the entire study. Then we also took up a very general outlook as to the model written as a triplet y, x, theta, sigma square I, and how the error sum of squares is coming, how the different sum of squares due to treatment parameters and block parameters are coming through the use of the projection matrix. And then at the end, we took up some questions basically dealing with the concept of connectedness, what happens if, etc., etc. And then we had some MCQs. So on the whole, one student can go through all these things and make sure that he or she has a grasp on these finer points in the context of a general block design. We will see what else is coming up next.
So here is the first one. In a connected block design involving B is equal to 7 blocks and B is equal to 7, that is the number of treatments, sum of squares of error was computed as 234.58 with 23 error degrees of freedom. Now the SS blocks unadjusted was computed as 68.25 and the sum of squares of treatments unadjusted was computed as 72.36. So we need to prepare formally the ANOVA table showing whatever computations are available. And the question is, which F statistic is larger of the two? Sir, will you explain the question a bit more?
So let's try to understand.
Okay, sir.
They are referring to a connected block design.
Yes, sir.
Involving 7 blocks and 7 treatments, but they don't mention the block sizes. So let's see, and the sum of squares have been computed. We have got the sum of squares due to error with 23 degrees of freedom and sum of squares due to blocks unadjusted and sum of squares due to treatments unadjusted.
Yes, sir.
Okay, prepare formally the ANOVA table. So do we know how much is there for the sum of squares due to treatments adjusted? No.
No.
How much is sum of squares due to blocks adjusted? No. All we know is that the treatment sum of squares, they don't even give the total sum of squares,
No,
isn't
sir.
that?
No, sir.
So I think in this question we need to have, it says prepare formally ANOVA table showing whatever computations are available. I think the problem is not essentially the problem is not complete. We need to know the total sum of squares.
Okay.
Imagine you have given the total sum of squares, then you can look at the sum of squares blocks unadjusted and then sum of squares due to error. If you take them out, you get sum of squares due to treatments adjusted.
Yes, sir.
And then when you have sum of squares due to treatments unadjusted, you can compute sum of squares due to blocks adjusted. So what is missing here is the total sum of squares. Yeah. But interestingly, they are saying that there are 23 error degrees of freedom. If error degree of freedom is 23, and because it is a connected block design, the block degree of freedom is 6 because there are 7 blocks, and the treatment degree of freedom is 6 again because there are 7 treatments. So 6 plus 6 plus 23, that makes it 35. Therefore, the total number of observations must be 36. That much we know. There are altogether 36 of the patients. What is missing is the total sum of squares. So we have to put a note saying that we have to assume certain value for that, and we know that has to be much more than 234.58 plus 68.25, as well as that has to be more than 234.58 plus 72.36. You will take the larger of the two and add something more to that, and then take it to be the total sum of squares. And then we can then go ahead and then compute the F ratios, and we can of course figure out which F ratio is the larger of the two. So it seems the question is a bit incomplete. We need to know the expression for the total sum of squares.
So we need to have some other values here.
Yeah, some other value. So only one thing is missing, for example.
Total sum.
We have to assume a computable value for that, and then the rest of the computation is pretty routine. Let's see the next question.
Sir. The next one is the replication of all treatments are doubled in a block design. So does it necessarily imply that the variance of the estimate of any treatment difference is halved? So we need to justify our answer.
Very good question.
So will you give us some
yeah, let's try to understand. You have a block design, and we assume that the block design is connected. Therefore, all treatment differences are estimable, etc., etc. And then they are saying that the replication of all the treatments are doubled in a block design. So whatever we had, the R1, R2, etc., everything has been doubled. So one way of doing it would be to look at the design, and then I shall keep the number of blocks intact, so only increase the block sizes, thereby doubling the replication numbers. We should start with a small example to see what is its implication on the estimates of the variances of the treatment differences. Whether does it really get halved because of double replication? So that's a tricky question. So you have to take up an example and see what it means in terms of whether the variance is really halved or not. It's a good question, conceptual question.
Yes, sir.
What is the next one?
So the next one is, in a connected block design, variance of estimated difference is computed as, the first one is between treatment 1 and treatment 2 and up to it's 2.57. And the next one is between treatment 1 and treatment 3 with 3.29. And the third one is between treatment 2 and treatment 3 with 5.34. So what can you say about pairwise covariates or correlations between treatment 1, 2 and 3?
This is what the question is. Very interesting problem. You have a connected block design, and let's assume that these are the only 3 treatments to be compared. We have the estimates of the variances of the estimated differences. We know the expression for the variance of the estimated difference between treatments 1 and 2, that is sigma square multiplied by C plus 1 1 plus C plus 2 2 minus 2 times C plus 1 2. That's the expression that we have from earlier representations. This is given somewhere in the module. So you have these expressions. So you have something equal to 2.57. We can ignore sigma square for the time being. So we have got 3 equations here involving C plus 1 1, C plus 2 2, C plus 3 3, C plus 1 2, C plus 1 3, C plus 2 3. We have 3 expressions involving these 6 quantities. We also know that the C matrix has got row and column totals equal to 0. So C11 plus C12 plus C13 equal to 0. Likewise, C plus 11 plus C plus 12 plus C plus 13 equal to 0, etc. We have a lot of information. So those we have to be used to make sure that we can compute pairwise covariance. We have to know what is the covariance between treatments 1 and 2, that is C plus 1 2. Whether we are in a position to compute the values of C plus 1 2, C plus 1 3 and C plus 2 3 from these expressions. We have to try it out.
So I will try it.
What is the next one? What is the MCQ?
So here comes the MCQ. Yes, the first one is the replication of all treatments are doubled in a block design. It necessarily implies that the variance of the estimate of any treatment difference is halved if
there are certain conditions given. Read out.
The first one is the original design can be thought of as an RBD, that is randomized block design, and the block sizes are doubled.
Very good. It says, suppose you have an RBD and all the block sizes have been doubled. And incidentally, in the process, the treatment applications have been doubled as well.
Yes, sir.
So, is it an example of a case where the variances of the estimated treatment differences is halved.
Is halved.
Or what is the second option?
It is the original design can be taken to be an RBD and it is doubled by duplicating or repeating the blocks twice.
Okay. So what does that mean? You have got B blocks to start with. You consider another set of blocks. Okay. Again repeating the B blocks. So the first set of B blocks forming an RBD, another set of B blocks forming RBD duplication,
yes.
and then take the two together. So in the process you get two B blocks.
Yes.
That is the option number B.
Yes.
And can you now show that the variance of the estimate of the treatment difference is halved?
Is halved, yes.
What is the third one?
The third one is the original design is arbitrary and the block sizes are doubled.
Okay.
And the fourth one is, this is the last one, the original design is arbitrary and the blocks are duplicated or replicated twice.
It's very interesting.
Yes.
The way to form the treatment applications to be doubled. So this each one makes sense in terms of doubling the treatment applications. But which one tells you that the variance of the estimated treatment difference will be halved?
Yes.
That's very interesting options. Okay. Now what is the next one? Okay, the MCQ. Okay,
so here comes the MCQ.
Yeah.
Yes, the first one is the replication of all treatments are doubled in a block design. It necessarily implies that the variance of the estimate of any treatment difference is halved if
there are certain conditions given.
Yes.
Read out.
The first one is the original design can be thought of as an RBD, that is randomized block design, and the block sizes are doubled.
Very good. It says, suppose you have an RBD and all the block sizes have been doubled, and incidentally in the process the treatment applications have been doubled as well.
Yes, sir.
So is it an example of a case where the variances of the estimated treatment differences is halved?
Is halved. Yes.
Or what is the second option?
It is the original design can be taken to be an RBD and it is doubled by duplicating or repeating the blocks twice.
Okay. So what does that mean? You have got B blocks to start with. You consider another set of blocks. Okay. Again repeating the B blocks. So the first set of B blocks forming an RBD, another set of B blocks forming RBD duplication,
yes.
and then take the two together. So in the process you get two B blocks.
Yes.
That is the option number B.
Yes.
And can you now show that the variance of the estimate of the treatment difference is halved?
Is halved, yes.
What is the third one?
The third one is the original design is arbitrary and the block sizes are doubled.
Okay.
And the fourth one is, this is the last one, the original design is arbitrary and the blocks are duplicated or replicated twice.
It's very interesting.
Yes.
The way to form the treatment applications to be doubled. So this each one makes sense in terms of doubling the treatment applications. But which one tells you that the variance of the estimated treatment difference will be halved?
Yes.
That's very interesting options. Okay. What is the next one? Yeah.
The next one is in a connected block design, replication of treatment 1 is reduced by 1 and that of treatment 2 is increased by 1. So would the design turn out to be disconnected? And there are three options. The first one is surely so, the second one is not at all, and the final one is maybe so.
Okay, so you are served with the connected block design.
Yes.
You don't know what is happening to that general connected block design. It has any arbitrary pattern. All you know is that the design is connected.
Yes.
Now suddenly for treatment number 1, you take out 1 and treatment number 2 you put 1.
Yes.
Now the question is whether the design is connected or not.
And
will it be necessarily disconnected? There are three interesting options.
Yes,
so what is the next one?
The next one is treatments 1 and 2 are exchanged in a connected block design.
Okay.
And the new design is necessarily, there are again three options, whether they will be connected, whether they will be disconnected, and it might be of other type of design.
So when it says treatments 1 and 2 are exchanged in a connected block design, wherever you have 1, you change it by 2, wherever you have 2, you change it by 1. Just switch the 2, that's the whole idea.
Okay.
Now what is happening to the new design? Very interesting.
Okay, sir.
And then